just to take a look at the schedule coming up. So because of this whole situation, things are a little bit spread out. If you were to have looked at the calendar spreadsheet yesterday or the day before, lesson 8 for this unit was going to be the last assignment for the first quarter, but it's just not going to happen. So lesson 7 is going to be the last assignment for the quarter, which I don't think really helps or hurts anyone tremendously. It's just good to know. And ton of people are going to be out on Wednesday, apparently. We're still going to wrap things up on Wednesday with lesson 7. We are not going to get the catch-up day. We're going to keep going with lesson 8, although every day is 20 minutes of catch-up, so not really any excuses. The last day to hand in anything, by hand in I mean late work request form, is Monday, end of day Monday, and I'm not taking anything after Monday. Fair warning. As far as these due dates go, I think they're still on track. Like anything, if a due date changes, it would only change in your favor. There is no recording yet for the lesson we're about to do, but there will be shortly, and hopefully it's this one. I won't have to redo it. Okay, so if you were to go to lesson 6, or I should say, if you go to current unit, you should be able to get into lesson 6. Please do that. Okay. So where we were 7th period, just to make sure you have access. Okay, so last time we did bottom up design process, where we started with the smallest problem first. If you recall, it was the diamond shape, where we drew the one step first, and then we used a few of those steps to do a side, and then the sides to draw the diamond. That was bottom up. We solved the first smallest thing first. We're going to do the opposite. And there's a couple things about going for the top-down design method. And one of the things is you can't really debug things until you are done, which is kind of a strange way of doing things. It also does require the ability to sort of visualize what's going to happen without hitting run, like to foresee things going on. And it might not be the way that you would solve something normally, but it'll be good to at least experience it. And by the time we get into anything complex, it's usually going to be some sort of combination of dealing with high-end stuff and then solving the low-end thing. So there are only 2 puzzles or levels for lesson 6. They're both a little bit longer compared to the other, drag one thing and you're done. The 2 are the 3x3 grid, which we are now going to be able to solve using multiple more efficient functions. And then bubble 2 is this one, which some places they call snowflake. And for each of these, we are going to do the problem solving process. We're going to work through it top down method. Because we have done this shape before, bubble 3, we've done it in different things. I'm going to work through that one right now, just sort of my own design process, which please follow along. And then once we've done that, I'll give you like a 5 or 10 minute heads up or head start on bubble 2. So we are going out of order for 1. We're going to do bubble 3. And if you're ever not sure where I am, there's clearly some bubbles up here. All right, so we're going to write a program that makes that shape, and we are going to think about the components, thinking about the biggest component first. First, let's go ahead and throw some white space on there so we can have some blocks. I do really, really, really want you, I'm going to make you separate your function definitions by white space. It gets too messy once we get into complicated stuff. Okay, so here is the way that it works. Top down, let's go ahead and call grid. Okay, we are calling a function that doesn't exist yet. And it's kind of a bit of a power move to just say, all right, call the function grid, function named grid. We'll solve it somehow, but it always feels like a real confident step to like just call a function that doesn't exist. But either way, this is our overall problem is grid. We've called it. Now we need to, well, we've named it grid. And a little bit out of order, we're calling it. And then we're defining it. And if we are going to define grid, break it up into its next logical chunk, I would say row is the next logical chunk. So let's go ahead and call a function, well, name it row, and call it 3 times. Okay, look, we're almost done. Not really. All right, so we've called the function row 3 times, which will make our grid. We need to define row. And not ROE, RW. And what is row made of? Well, row is made up of 3 squares. So let's go ahead and call square. And call it 3 times. Okay, so a row is made of 3 squares. We just need to draw a square. Okay, we have called square. We need to define it. So our function square just needs to draw a square, which is forward, left 4 times. Now, this is clearly more complex than just that. Although at this point, calling grid is going to call 3 rows. Each row will call 3 squares. Each square is a full square. We're going to draw 9 squares. Just the problem is that they're all on top of each other and to the top left. First thing I notice is that I want all of this to be up and to the right of where I am. And so even not knowing where we're headed, I would like a right turn function. I think it'll just be convenient at some point. I'll probably need it a couple times. So I'm going to define a function named right. It probably won't let you call it right turn, or it usually doesn't, because that name is reserved for the turn right function that they're hiding from you on purpose at this point. So right works for us now. And our right turn function is just going to be a triple left. And anytime we want to turn right, we'll just call right. It's there. We never have to think about the fact, we never have to think about how it accomplishes the right turn. We just know we have a block that will make the turtle turn right. There's a delicate balance between showing you all the pixels and making sure the pixels are large enough to see. I'll try to scroll slow, and this is sort of a in-between zoom. Okay, so first thing, before we solve the 9 squares on top of each other situation, I definitely want to set it up so that I can maximize my number of left turns. So I'm going to start before anything happens and just call right. So at least it'll start with my setup. It'll start out pointing east so that I can do all my left turns. Now, the next step is we need to figure out why each square is on top of each other. And here we're going to do a little debugging by commenting out some things. We want to figure out how square works, or rather how square works within row. We don't want to call the full grid yet because it's just going to stack a few rows and it'll be difficult to solve. We just need to solve one row. So what we're going to do is not call grid. You can do a couple things. You can comment out, where in any text mode, and really in any text editor outside of here, if you have your cursor on a line and do Control/, it comments out that line, which deactivates it, which is super useful because it's better than just deleting it and bringing it back. you can comment it out. You can comment out many lines at the same time by highlighting and control slash, although we don't need to do that yet. What we need to do is just comment out and, oh, shoot. Comment out grid, or at this point, you really could delete it because it's just one line. So either way, getting rid of our overall call will prevent this from being called, and that will allow us to solve one row. And so I'm going to call row in here just so I can solve one row with the purpose of stacking the rows. So the reason why the three squares of a single row are on top of each other, because it doesn't set up for the next square. We need to add a move forward at the end of square so that it's ready for the next one. Okay, and if our row situation starts out pointing east, ready to draw itself, we need to have the function called row end here pointing east, so it's ready to draw our row again. And if we set it up right, that means the next time it'll be back there. And just for the sake of organizing, I'm going to make a function called reset, maybe. And its only job is to get the cursor from here pointing east to here pointing east. And it's not going to be super elegant code, but it's going to be easier to just call reset when I need to. So let's name it reset. And the code to go from here, I need a left turn. I need a forward. I need another left. I need a triple forward. Jeez. Triple forward. And that should have me point over here, pointing west. And so that means I need a double left. Okay, so reset is what happens after the three squares. So all we need to do, we can either put reset here, so it's like square, reset, square, reset. Oh, no, it wouldn't be square reset. It'd be row. It would be row reset, because the reset happens after we draw one row. And just to test, let's I am going to actually comment out these, so I'm only drawing one. And if this this sort of debugging, commenting out thing loses you, just hang out. We'll get back to the regular thing. This all can be done without debugging. I mean, without commenting out. Uh-oh, let's go like this. Okay, so right now I do have my grid calling, but it's only calling one row and one reset. We're hoping it gets back to the ready for the next one. Beautiful. Okay, so this is where it's going to start. Settle down. If you have a question, you can ask it. But at this point, we're going to turn off or comment in my other row reset, and now it should be able to do the whole thing. And from here to get back, I mean, we could just hard code it in. It's just so awkward. I don't know. There's so many different. We could make another function that was turn left, triple forward. And where does that put me? That puts me at the origin, pointing. Oh, no, I need another turn. Oh, well, this is just a right because we're facing east. Triple forward, and then I think double left. So there's certainly some clunky parts. This triple forward, turn left, I think shows up a couple places, so it probably could be another function. And yeah, so here's another triple forward, double left. It's a lot, choosing a good function chunk of code that will be a useful function is a lot like when we did the text compression thing. The longer the dictionary entry and the more frequent it happened, the better dictionary entry it was. But at this point, there's something to be said for the fact that we're done. And we don't really need to refactor and make it cleaner because we're not going to use this program code in a bigger project. It's just sort of done. So the takeaways of top down are naming the problem, naming the overall problem, then defining its pieces, which was row, and then defining the pieces of that, which is square, and then solving the lowest one. What we're doing. Okay. So go ahead back to bubble 2. Why can't I go back? There we go. Back to bubble 2 and think about how you're going to break this down. Okay. They call us snowflake. That's fine. Okay. There's a couple ways to break down the second layer. Obviously, the top layer is the full thing, snowflake, but you could break this into 4 crosses that are 90 degrees apart, in which case you would just need to solve one of the crosses. You could define it as 5 plus signs. Okay, there's a few ways to do that second level, but whatever you end up with that second level, you need to break it into the third level, which will probably be some sort of branch or stick or edge or whatever. Okay, I'll give you 10 minutes, but so far every other class has either been done or given up after 5 minutes. So let's go, we'll call it a 5-minute timer and then how much I forget to stop it. All right, let's take a look at this. All right, the plan for this one, just break it up into chunks. The first one is going to be draw a snowflake. And let's do some white, throw some white space on there. And so our highest level function is definitely snowflake. I'm done with calling things draw snowflake. So we're calling it, let's define it. Snowflake. I would say it is just cross 4 times. Cross is the function I'm currently defining. Okay, so cross is just one of these branches, or one quarter of it. Okay, there's 4 of them. So now we need to define cross. So cross is each one of the crosses. I see it as 3 branches. And the branches are all going to be out and backs, like forward and forward, double left, and forward again. So let's start with cross being, I think, branch 3 time will work. 3 time BRANCH. But I'm not sure if that's good. I don't think that's going to be enough. So let's go ahead and figure out how to do one branch. So branch is definitely forward, double left, forward. That'll be one thing. And if we call, I'm actually just going to use my top level call to work with cross here. And so if we call cross, it should call 3 branches. And this is our sort of main mid-level function that if we can finish this once, we can go straight to snowflake. So if we do this once, okay, clearly it's just doing back and forth. And that's because we need an extra turn at the end. And that'll set it up for 90 degrees apart. The problem is this one, the one that I'm planning, is this top center one that I want to end with a ready for the next one. And I also currently am starting here, and I don't want my first thing to be here. I want it to be here. So we're going to start with a forward, forward, and left. We're going to have the cross start with forward, forward, left. Excuse me, forward, forward, left to set up 3 branches. And let's see what happens. Okay, so forward, 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 left is just the part that gets me to the intersection of the cross there. And then branch, branch, branch. Now, in order to be ready for the next one, I need to have it go down 1, 2, and turn left, which I already have a forward, forward, left. Why not make a function? And what's a good name for this? How about recenter? Reset. I like recenter right now. And recenter is just going to be these 3 lines of code. And then all we need to do is call it. So across is going to be recenter to get to where we started, and then 3 branches and recenter again. So there we go. 1 branch, 2 branch, 3 branch. And now it's back at the origin, ready for the next one, which means we can just call cross 4 times, otherwise known as snowflake. Okay. If you missed the code for this, it will be in a replay shortly, and you can work through that if you want. the key takeaway from this is the problem solving technique of starting at the top and figuring out its components and figuring out its components and solving that and working your way back up. Okay, that's top down. It allows us all of these beautiful layers and abstractions. All right, so that's it for the activities. There are 4 checks for understanding of varying complexity. And okay, so throughout the checks for understanding throughout the lessons, the curriculum, you will see some check for understandings that refer to the performance test. I'm sure I've said it a dozen times before, and that's fine. I'll say it more. The performance task is the project we do in the spring. It's usually okay. The performance task is the project that we will do in the spring. Everyone is going to do it. There will be plenty of time in class to do it. You will have the skills, as long as you are in here doing work, you will have the skills to make it very easily. Just a heads up, the project is you're making your own program sort of from scratch. It does not have to be difficult. It just has to have examples of abstraction, an example of a conditional or a list or something like that, which of course we haven't talked about yet, but that's the point. And the rubric for it is made up of 6 rows, for which each row is either you get the point or you don't get the point. So your goal is, of course, 6 out of 6. And the rows technically have to do more about the writing response that you're writing about your program. It's all sort of tied together. And like I said, plenty of time to work on it in class, plenty of time between now and then. Don't sweat it. The thing for here is they are trying to get you to write with the prompt about the development process and, iterative design and sort of overcoming design challenges. The concession for this practice response is that the prompt is designed for a larger project where you discuss things, hurdles that you've overcome throughout making the project. And this was a 10-minute practice thing. The point is to practice writing about your development process. And for any of these, they say to make the 3x3 grid program, it actually makes more sense to write about the snowflake, but you could write about either for this. Okay, bubble 5. So this completely new design that, did they even give it a name? I don't know. And your only job here is to think about how you would break this down into smaller components. Okay, you just need the names of the functions. If I was doing the same writing prompt for the grid, my answer would be, well, what's my top level function? Grid. And when you're writing out the name of a function, throw an open close parentheses on there just so you know. My next level function was row, and my next level function was square. And that's it. That's it for this writing prompt. This is not your answer, just to be clear. This is the answer if the shape was the grid. You need to come up with, essentially, invent names for how you're breaking this down. There's clearly a lot of straights that could probably be in a function. There's some repeated turns. Obviously, you need to define the entire thing. But that is bubble 5. And bubble 6, which of the following statements about writing functions and top-down design is not true? Okay, writing functions help manage complexity in a program. They absolutely do. That's sort of their main job, their defining characteristic. They make it easier to write the code because you're sort of making your toolbox. Writing a function is like putting a tool in the toolbox or a plan, whatever. Code you don't have to write over and over again. Top-down design leads to programs which feature multiple layers of abstraction. Absolutely. It's what we just did. Okay, breaking things down into chunks and logical chunks and farther down. That is how you get abstraction, or that is an easy way to arrive at an example of abstraction. Okay, bubble C, or whatever. Answer C. Two programmers solving the same problem using top-down design should arrive at identical programs. Absolutely not. There are many ways to solve any problem, but these problems included, that would not end up with the same program. Well, certainly not. Okay, so that's the false one. Let's look and see if there are any falser ones in case I misread. That's always been a good technique. Top-down design relies upon identifying subproblems of a larger problem. That's redundant with this is layers. And top-down design assists in identifying the layers of functions that we use in a program problem. All of the wrong answers, all the things that are true of here are sort of different ways of saying the exact same thing. But hopefully you grasp the concept. Okay, and abstraction to manage complexity. In the performance task, you'll be asked to identify abstraction. In your program, explain how to manage complexity of program. Functions are a form of abstraction. Pick a function you wrote for either of the things that we just did, either the snowflake or the grid, and explain how it manages complexity of program. One really good or two mediocre sentences should be enough, as long as it's correct and complete. That's what we're going for. Okay, I'll give you 5 or so minutes to put some